So my talk is going to be about cloud native, and I may say again, but it's going to be totally different focus. It's going to be a perspective of a software engineer. So maybe let me start with a little bit of who I am, what I'm working on, so that you get like the context for my perspective on cloud native. Okay, so I'm an engineering manager working at Google. So first of all, let me check a little bit of the background knowledge. Which company built Kubernetes? Who thinks it was Amazon? Okay, good. It's not that bad. Like, who thinks it's Google? Okay, good. So we know about that. All right. Who knows that Kubernetes is actually being developed in Warsaw, in Poland? Wow, amazing. Okay. So for those who did not raise their hands, so I'm actually managing the Kubernetes team within Google that's based here in Warsaw. We are obviously part of a bigger organization. How big of a chunk we are? So Kubernetes, if you look at the open source community, there is, I think, around 23, 24 so-called special interest groups. So the whole community is kind of organized in those groups that are doing development of specific components or specific features or qualities of Kubernetes. Like 3 of those special interest groups are actually led by engineers here in Warsaw. These are actually quite important interest groups. That's scalability for Kubernetes, instrumentation, and autoscaling. Okay, but I think the more important thing that for this talk, even that I'm managing the Kubernetes developers team, is that I joined Google in 2007 as a software engineer. And that was really an amazing experience, mind-blowing, because Google has been doing everything totally differently that that I've seen before working as a software engineer for other companies. Basically, Google built everything their own way. And right now, like fast forward, 12 years later, it's really fun to see that people are calling these ways cloud native. So I will tell you a little bit about, so this talk is going to be a little bit about software engineer perspective on what cloud native means. So what cloud native means to me. So basically, first, what is cloud? So I have a very ignorant, simple definition. Whenever you have not one machine, not one computer, but a set of computers, and possibly interconnected with the network, some storage devices, and you have not one application, but a pool of applications, and you want to deploy those applications on those computers. That's cloud. Like at the time when there was only a single computer, this problem has been actually solved by an operating system. Right? So operating system was this thing that basically guaranteed that if you run multiple applications on a single computer, the stuff works. That each application, for instance, will get disjoint area of memory assigned to it, right? And they will not kind of interfere with each other. So now with the distributed infrastructure environment, the problem is well, much more difficult. So now let's add a word native to that. So for a software engineer, what cloud native means to me is how to actually build software so that it is prepared to run on this distributed environment. And yeah, so that's it. And then let's take a look back into the history. So I'm scrolling back like 20 years ago almost. This thing right now, this is like how Google looked like 20 years ago. And this is, by the way, the CRT monitor, for those who don't know what's this device. So Google was a startup back then. Google wasn't rich like it is right now. So Google decided to build the infrastructure by basically gluing together a bunch of PCs and running open source Linux operating system. That's like the cheapest that you could get. And the stuff wasn't very reliable, by the way. Specifically, if you think about like years like 1999, Linux, it wasn't reliable. Like the enterprise-grade commercial distribution of Linux was like Red Hat in 2002. And yet, with this cheap hardware and operating system stack, Google had to deal with quite big growth in scale. So, like for instance, I think it was like around 1999. I think in 5 months the queries per day to Google grew from like 50K to 500,000, and all on those PCs, the cheapest we could get. So basically, Google had to figure out how to build for scalability because of the growth, and availability because of not mature enough stack, let's say, and not reliable enough stack underneath. So Google started building like an all new way of thinking how to build applications for scalability and availability. Instead of hardening the hardware, buying expensive super servers, write disks, whatever, they said, okay, failure is a norm, design for it when you write your software. And so a number of things had to be built from scratch. So maybe you remember, back from the year 2000s, there was a number of really interesting papers published by Google about fundamental building blocks for constructing applications that would run in cloud. So that actually distributed applications. So obviously, the key to scalability is run on multiple machines because the machines were small, and the key to availability is also multiple machines because one machine can fail. So, for instance, there was a paper called the Google File System. So this is a distributed file storage. So for a software engineer, as I was back then, it was like super cool to me. Like it looked like a regular file interface, like for a local disk, except that the files that I was writing were actually stored in a distributed storage. That means every file was sharded into multiple chunks and stored on multiple computers. That's for performance and scale, right? Because like the throughput of disk is only certain, and then if you can chunk the file into multiple shards, you basically multiply the throughput of the reads and writes. And also each single shard was replicated at least 3 times for durability and availability. And I was just using, kind of regular file API. Then there was a number of more advanced systems built on top of that, like the Bigtable. So that's like a structured storage, again, replicated, sharded, so distributed storage for structured data. Going up the stack from the storage to compute, MapReduce. Really brilliant framework for parallel computing. Very simple, yet super robust. It kind of builds on top of, it uses, our implementation of MapReduce, the early one obviously used GFS, etc. So when I joined Google in 2007, it was like, wow, so I can right now basically calculate more prime numbers than, that are known to the world yet if I just, stitch together like a few lines of code and deploy a MapReduce into Google Data Center. So finally, remember, the whole thing about cloud is that there is this distributed infrastructure. We have multiple machines. We have multiple pieces of software to install on those. Specifically, we need those machines for scalability and availability. So there is this complexity of how to do this. You don't want to kind of SSH to every single machine and deploy, right? So Google came up with this system called Borg. So there's another paper published. It was published actually quite late, but the system has been in operation since like early 2000s. And you can see that some things are familiar. Like this system is basically about managing a pool of machines together as a cluster. On every single machine in the cluster, there is an agent software called Borglet, and there is a logically one master machine called Borgmaster, which manages deployment of software onto the other machines in the cluster. So this basically let us easily, as a developer, it was super easy for me to kind of deploy my code onto whatever, 10,000 machines. It wasn't a big issue. Now, the fun thing is that some of these people who are on the author list of this Borg paper are right now, like, we're actually working with them right now on Kubernetes. Like David Oppenheimer, Eric Thune, these guys are right now on the Kubernetes team. So if you ever join the Kubernetes team in Warsaw, these guys will be doing design reviews for your design docs. So now so fast forward now into like more recent years. So my claim is that what used to be a design choice by Google, that we're gonna buy this crappy hardware and really immature Linux operating system, and therefore we're gonna design everything so that it kind of deals with failures. That was a design choice. Right now is a kind of necessity. And why? Because first of all, the scale is even bigger. Whatever industry you're in, the demand for computing power is only growing. That's one thing. And the other thing is that whatever industry you're in, you're most likely you need to design for scale, for large scale, because very competitive environment. So the only way to actually earn money is to have a large scale. So even if you look at like Polish startups from the early 2000s, they were not thinking about the global market. Everything was about local things. And only in the last couple of years, we see startups that from scratch are designed for a global market, and are actually successful. But then they need to design for scale. So right now it's a necessity. Also because the advancement in computing power of individual CPUs is not as fast as it used to be. While the demand for computing power is still growing very fast. So basically, that means that the distributed computing and designing software to run on multiple machines is basically a necessity. And not surprisingly, we've seen like the popularity of Kubernetes, which is only one of the tools that was kind of transferred from proprietary Google implementation to an open source implementation for the whole world. Obviously, you must have heard about Hadoop and all these things, which are implementations of the previously mentioned systems. Okay, but this is the tool. Now, I would like to focus a little bit more the rest of this talk on actually design principles. So this is really targeted mostly at software engineers, but not only. At developers. So the first most obvious is use redundancy. So I think we already talked about it, that we need to run on multiple machines for scale and for availability. But then let's get a little bit deeper into the details of this. It's not that trivial. So obviously you should be designing your systems in a way that as much as possible of the services are stateless services. So basically like have storage aside and have all the logic in stateless services. If you have stateless services, they are super easy to scale and improve availability at the same time, because you basically spin up more replicas of the same binary. And if it breaks, it breaks. That's not a problem. Like some other replica can basically handle the load because there is no state that needs to be transmitted or lost if the replica broke badly. So really prefer stateless, but it's not always possible. So, for the kind of compute services that need to carry some state or cannot really run independently as kind of totally independent processing units, there is a design pattern called master election. So you pick one of the replicas that is kind of leading whatever job the software needs to do. So for instance, so I used to say that 20 years ago, how I recognized a really good software engineer is if they really understood well quicksort, for instance. And why is it n log n actually and not n squared? Because it's not obvious if you start thinking about the canonical implementation. So right now, I would say in modern times, cloud native times, if the software engineer understands Paxos algorithm, that is a good signal, right? Because that means, they understand how the distributed systems work. And, by the way, this is something that Kubernetes will not do for you, right? It's not a tool. It's like how to build software. Like if you write a software in Kubernetes, it's not like it suddenly will become a stateless or it suddenly will get master election with Paxos implemented inside of that. So speaking of high availability, because a lot of that design pattern redundancy is about availability, Kubernetes does help us a lot, but it doesn't do all the job, right? So Kubernetes introduces a couple of failure domains. A failure domain is basically kind of like a blast radius. So you should expect two separate failure domains to have uncorrelated failures. So in Kubernetes, container is a one failure domain. If it fails, a single replica of your application, single container running somewhere, kubelet on that node will respawn it. Then the next failure domain is a node, is a machine, virtual machine or physical machine, whatever you run. Again, Kubernetes handles the failures in this failure domain. If a node fails, Kubernetes will see it's unresponsive and will reschedule all the pods, all the containers to a different node. So that's great. There is also next level of failure domain, which is associated, if you're running in public cloud, it's associated with public cloud provider infrastructure. So most of the public cloud providers have some notion of availability zone. Like in Google Cloud, that's called a zone. And we usually have number of zones in a region. So region is really meaningful semantically because it's like location, geographical, and zone is just our failure domain. So through the way we do upgrades, etc., we kind of guarantee that we will not break more than one zone at the same time. We should not, again, at least. So, so the hosted Kubernetes platforms, they typically offer some sort of spreading across multiple failure availability zones of public cloud provider. So for instance, in GKE, obviously you can have a replicated master. So a Kubernetes master will be running in 3 different availability zones, and it can manage nodes across these availability zones. And as a matter of fact, the Warsaw team actually built the replicated masters for GKE. It basically uses the etcd replication underneath. The kind of front ends, kind of API servers are just load balanced, and controllers that need to run only one of those can run in parallel. They are master elected. So it's kind of combination of the design patterns that we just talked about that we have implemented here. But there is also some very important consideration that impact the availability of your services that are beyond Kubernetes. Just using Kubernetes will not help you. First thing, very important, canarying. So canarying is about introducing change gradually to your user base, right? So you want to introduce like a new version of your app, and you want to, let's say, reroute only some small percentage of the traffic to this new version. And if something goes wrong there, you really kind of roll back really quick. Kubernetes doesn't support it that well, right? Kubernetes has the deployment controller, which will do rolling upgrades. But if, let's say, you have 10 replicas of the application, that means if you start doing rolling upgrades, you don't have fine-grained control. One replica you replace with the new version, and 10% of traffic you may expect to go to a new replica, but maybe you want 0.1% of the traffic to go to the new replica. So for that level of control, you need to use additional tools on top of Kubernetes. Good example here is Istio Service Mesh. Next very important design pattern, avoid cascading failures. So you have to distribute your redundant replicas across failure domains. You also should, if you actually can afford it, because it comes with a cost. You should build the system in such a way that if something breaks in one of the failure domains, let's say availability zone breaks, like one of the GC zones at Google just goes down for a couple of hours or whatever. You should not expect your system to do reactive failover, because what it means that in the failure condition you are generating a lot of unusual activity in the systems that probably they were not tested well for. So a lot of churning the API servers. You need to basically suddenly reschedule all these pods that were there into other nodes, and maybe there is not enough nodes in the other availability zones, so you need to with Cluster Autoscaler you can create more nodes automatically, but still there is like a churn in the system. Kind of a lot is going on exactly at the time when the system is having hard time. So instead of that, you should do over-provisioning. So you should calculate that, if one failure domain fails, the others should just be able to serve the traffic. For instance, if you're using 3 availability zones at Google in a single region, if you need 100 replicas, you deploy 50 to each zone, so you have 150. And if one fails, you still have 100. So you don't have to do anything. Load balancer will just reroute the traffic and you're done. So obviously, the more failure domains you have, the cheaper the extra cost is. If you have 3 availability zones, the over-provisioning factor is 50%. If you have 4, that will be 33%, etc. All right, back to the thing about distributing stuff, redundancy. We talked about stateless. It's trivial. With stateful compute, a little bit more sophisticated, maybe use master election. But what about the storage? So storage is really difficult. So my recommendation would be use managed storages for distributed systems. But if you need to pick some solution, very good guidelines would be go and read CAP theorem and kind of understand the properties of the systems, the fundamental distributed properties of those storage systems. So CAP theorem talks about the thing that you cannot optimize for these 3 letters at once. The C stays for consistency, which is basically all your replicas will have the same values. A stands for availability, so that's pretty obvious, and then P stands for partition tolerance. So in the distributed system, what happens if the network connectivity goes down between maybe your availability zones, for instance. And so the CAP theorem says that you really cannot optimize for 3 at the same time. You need to sacrifice on one of these dimensions. And in various use cases, the design choice may be different storage system. Google, for instance, has a very nice managed solution called Cloud Spanner. So Spanner internally is our distributed SQL-like database. It's actually globally distributed, globally replicated, and it gives you it kind of imitates that the CAP theorem doesn't exist. It looks like it optimizes for all of them, but really what happens is that A is just quite high because of the super reliable network. So Google has basically owns end-to-end the networking components that connect these distributed sites, data centers across the world, and there's a lot of redundancy built into the networking infrastructure. But it really is not 100% available. It's like internal implementation Spanner is has 5 nines, which is quite amazing anyways. Okay, so cloud native, we already covered the aspects of scalability and availability with certain design patterns, how to build software so that it can run on multiple machines in a distributed environment in a scalable and available way. But this is not all of that that we are expecting from cloud native. So you've heard from Pini, his great talk that actually velocity is super important. Cost efficiency is also important actually. So so this is my favorite slide for explaining specifically to enterprises why velocity is important. This shows on average how many years companies who joined S&P 500 index. This is the index of the biggest companies on the biggest stock exchanges in US. That's New York Stock Exchange and NASDAQ. It's how many years took on average the company that joined this index, that got there that high. And as you can see, it was like 75 years in the 50s, and right now it's only 10 years, which means that kind of startups will get there in 5 years from now, probably, or can get there. So if you combine that with the fact that a lot of competitive advantage right now is in software, actually, in multiple industries, even in traditional industries like banking. Like, for instance, I'm choosing my kind of bank to a large extent by how good are the online services, how good user experience they have on their mobile app, etc. So basically, everybody competes in software and needs to move fast. So that's why velocity of developing new software is super important for everybody. And cloud native so far doesn't seem like it's solving, right? It's kind of adding new problems. It's kind of scalability, availability, multiple failure domains. So that's why So that was a must, but this is like a good, so scalability is a must, but then this is an important requirement, and that's why people built a lot of features that should make it actually easier and faster to develop distributed software. Because by no means writing distributed software is faster than writing a single-threaded application unit you run a single machine. That's like a myth. So, first thing was containers. How containers help? Well, first of all, there's a lot of agility with developing with containers because you can easily deploy on various infrastructures in various environments. You package everything. You package your software with all dependencies, so all this complexity of managing dependencies, library versions is gone. And isolation, so there is more kind of reliability with regards to whether this application will not eat up all the memory that was intended for this other application on this machine, right? So containers definitely help. Kubernetes here obviously is orchestrating deployment of containers, so helps. There was actually an amazing talk on the KubeCon in Barcelona, if anybody was there this year, from CERN in Switzerland. They have rerun the computations that led them to the Physics Nobel Prize in 2013 for discovery of Higgs boson. So basically, they took the same computations, they rerun it on Kubernetes cluster. And what they said is, what's amazing is they, with containers, they package their code with all dependencies, and they can finally rerun the scientific computations exactly the same way as this was run like 7 years ago, back in 2012. And this was a huge thing for them for some reason. Okay, but containers, not enough. If you just put your big, huge monolith into a container, it doesn't help you much with the agility of the development. So the key here is, to architect software so that it has small microservices. I think this idea is nothing new to you. Just wanted to remind that this is still important. For availability reasons, limited blast radius. For cost efficiency, it's easier to auto-scale because maybe only one microservice needs to auto-scale, not everything needs to auto-scale. And obviously agility of the teams. So small Scrum teams focused on the small components with well-defined APIs, contracts. Easier to do faster rollouts because if you create a new build, there is some test fails, you don't need to find a regression in thousands of change lists that happened since the previous release, but maybe just a couple of them, and it's super easy to find and move on. So again, this is something that Kubernetes per se is not solving, right? You need to figure out your CI/CD story, your architecture for your applications, most importantly, and then maybe introduce some additional frameworks such as, again, Service Mesh, Istio, to manage those microservices. Autoscaling is, on the other hand, something that Kubernetes gives you out of the box. So there's a lot of features in Kubernetes to optimize for cost efficiency. So you have horizontal pod autoscaler, vertical pod autoscaler, cluster autoscaler, everything developed in Warsaw. And this one is actually super important. So what is SRE culture? So I guess you guys are familiar with the concept of DevOps. SRE is like Google implementation of DevOps that's focusing on reliability. So as a software engineer at Google, I've been working many years together on the projects with SREs. So SREs are the people who are responsible for running production systems. But it's not like software engineers are building the system and then passing it to SREs and go and kind of take care of that. That would be a nightmare for SREs. Instead, it's a close collaboration even in the design phase. So SREs are reviewing the designs of the software that's built by software engineers, specifically for things like whether this software is applying good design patterns for building distributed software. So that it can actually scale, it can actually be made highly available, and there are no architectural flaws that would prevent that. These are, I think, my kind of real quick private view on what are the most important things from the SRE culture. First of all, roll out fast, roll out frequently. And do it everything automatically, and as you do it, measure what's happening. basically, vast majority of the outages that I've seen in Google Cloud and before Google Cloud in Google were caused by some change, introducing configuration change or introducing a new version of the software, new version of the component, new code. So therefore, it's super important to have this team that is actually making sure that everything that is developed is adhering to certain best practices. So there is proper monitoring in place. There is proper canarying process that I have already mentioned, right? And most importantly, blameless post-mortems culture. This is like super important. This is about making sure that there is no like finger pointing and who did something wrong in case if there is an outage. Instead, there is a culture of doing a deep and thorough analysis of what has happened and why that enables the team to improve the processes, improve the designs. If that would be finger pointing, that wouldn't work because everybody would be afraid of bringing new pieces of information into the discussion because maybe this piece of information would guide somebody into, oh, maybe that was your fault, right? And this is with blameless culture. It doesn't happen. Everybody brings up everything they know, and the company is able to improve. All right. So to sum up, these are, in my opinion, like the 5 kind of transformational ideas that we were discussing. First of all, distributed computing for scale and for availability. Then to manage that then to make it in manageable tools like containers, Kubernetes for container orchestration, and even further up the kind of abstraction layer, service meshes such as Istio. And I really highly recommend to read a book about the SRE culture. I can't even remember the title. I know it as the SRE book. It's called, it's just Site Reliability Engineering. It's available for free, actually, on Google Books page. And this book has also a lot of these design patterns for distributed software inside. And again, my idea for this talk was to kind of explain that, how you architect the software is ultimately the most important thing. The tools like Kubernetes are only kind of supporting you in that. And only that, if you are really designing this stuff well, you can kind of shoot for these 4 properties that are kind of expectations from what cloud native should give us. So scalability, availability, and still reasonable cost efficiency and high velocity. I'm going to finish with a quote from a director of engineering at Spotify, who basically believes that this cloud native is really helping his company to focus on bringing, the value added. So Spotify, they're really about music recommendations, and kind of working on the infrastructure, cluster managers for data centers. It's not something their business is about. So thank you very much. There is some context to me, LinkedIn, my Google email.
So my question is simple. What about security? Because we don't see any slides about security, and it's very important here.
Yes, I wasn't focusing on security. My focus was more like how to build distributed systems, but security is like super important, that's definitely. And this is, again, something that Kubernetes by itself would not solve for you, right? So, of course, there is a lot of advancements in the security area in Kubernetes. For instance, things like secure pods in GKE. But then, still, you have to think about how to use these technologies. Yeah. So
what about multi-tenancy in apps?
Yeah. So multi-tenancy is a hot topic in the Kubernetes world. Because of number of things, enterprises kind of expect that there'll be like multiple teams running their stuff in Kubernetes clusters, and there's going to be some cost attribution. SaaS providers are looking into ways of having better economy, like basically an approach where they would create a Kubernetes cluster per instance of their service kind of is not economically great. So they're looking into running multiple stuff in a single cluster. And Kubernetes, frankly speaking, was not very well designed for that. So, so there's a number of efforts in the open source, and also specific cloud providers that have managed services are introducing new advancements in those areas. So, for instance, there is a discussion right now about the hierarchical namespaces. There is so, for instance, in GK you have recently introduced advanced metering, which lets you kind of do cost attribution to namespaces. There is also a lot of work that's put into the area of basically better isolating the software components that are pods basically, and even not so much pods between themselves, but also between the boundary between pods and the system components such as kubelet. This is very tricky. So so I think one thing is things like gvisor and secure pods. But like in general, right now most of the times people are still choosing kind of multi-single tenant architectures where they would run a cluster per instance of something if this is really critical to have this well isolated. But the progress is being done, as I said.
Was wondering if you could comment on progress made on stateful workloads.
Oh, I don't know much in this area, so sorry.
I recently saw the movement of the splitting Kubernetes into the different clouds. For example, we can see OpenShift, GKE, and now, for example, VMware is doing actually their own custom solutions. How do you find it right now?
Well, so you mean like running Kubernetes in various heterogeneous environments, like you have, let's say, Kubernetes instance on-prem and on Amazon and on GK or something like that, right?
Sorry, I should explain better. Because right now I can see that you can find different implementation of Kubernetes. Like OpenShift is different than GKE.
Oh, yeah, right, got it. So I think it was like a year and a half or 2 years ago, the big thing that we were working on in the open source community was conformance tests. And it's there. So right now there is conformance tests, and you can claim that your Kubernetes distribution or managed service is actually conformant to Kubernetes standards. So and yes, that's totally fine. Like different vendors want to find their differentiation, maybe provide better implementations for some APIs. But that's why we have these conformance tests to make.
I thought that some 30% of the core Kubernetes developers were here in Warsaw, but you said only 3 of the team leaders were out of 23.
Not 30%. I think it's a little bit less. I mean, it's definitely 2 digits, but it's hard to quantify for me exactly right now because these boundaries are blurring, like whether guys who are working on Istio and introducing some changes to networking, like it's but I think core Kubernetes is a little bit less than 30% here. But 3 special interest groups, that's
But why not more special? Why isn't more stuff being run out of Poland?
Come join us and we can hire more. Like the issue is hiring basically. And you may also ask yourself, why the heck did Google build a team that's building Kubernetes in Warsaw and not anywhere else in the world, where the history of that is basically we were working on a number of internal solutions, for Borg, for instance, and at the very beginning, Kubernetes was kind of experimental, innovative project, and just, engineers from here joined together with some engineers from Mountain View and kind of built the prototype, and that's how it started.
So, answering the previous question, you mentioned that there are some people working on Istio. What's in Google, I take it? Mm-hmm. What are they working on explicitly? Like, are there plans to incorporate Istio functionality into Kubernetes? Or
dangerous area. I'm not sure what I'm allowed to talk and what not. Sorry.
Anybody else? We can still fit in at least one more question. Scanning.
I mean, future product areas, right? I'm not like. First of all, I'm not like and the source of knowledge, and second of all, I'm not sure which are public informations, which are not.